Hello and welcome to, I think it's episode 6 of Bragi. Uh, might be a pretty short episode today as well, but we'll see how it goes. My idea for today was to try to optimize our filtering or sample rate conversion a little bit. There are probably a lot of things we could do, but one of the very simple things that we can do is when we're doing the filtering, which we basically have here is a double for loop. So for each sample in our upsampled signal, we go over, we iterate, n number of samples again, starting from that sample and then going forward. And the n is equal to the length of our filter. Um, so just by looking at this, there's much we can do. If you don't know the values of what that we're dealing with here. But what we do know is that our upsampled signal, we upsampled it by zero stuffing, right? So we insert a bunch of zeros basically in our upsample signal, or in our original signal, then we get our upsampled signal, which means that down here, when we're iterating over, the length of our filter and accumulating or summing these basically, a lot of them are just going to be zero because the data in our upsampled signal, most of those samples, depending on our upsampling factor, but most of the time, more than half of those are going to be zero. So there's really no point in doing multiplications or doing any work with those because they're all going to be zero. Even though the filter value is not going to be zero, something multiplied with zero is zero, so we're not doing anything really. So, of course, there are multiple ways of doing this, but I think I would just want to do a very simple version first. Now, since we want to optimize this a little bit, it's always good to try to measure first and then measure afterwards. So, I've never used this tool before, but there's a profiler called Superluminal, which you can buy. And there's a 14-day trial which I've downloaded, which I'm using here. So I actually went ahead and built Bragi in release mode for the first time and ran it. We don't want to be running in debug anymore. I want optimizing, at least this stuff. So I built in release mode. I made a capture. I also named it threads, so it's a bit easier to know which thread we're looking at. And so basically what you're seeing here is, the startup of the main thread, and then probably pretty much nothing is happening. I'm just writing in, play this playlist, and then it loads the first song in the sound thread, and then it starts doing the sampler conversion. So you can see how it's taking quite a long time. So we can see here that the main thread is blocked for about 7.5 seconds, while basically all of that is doing the sample rate conversion. So we can see here, if I open this thread here, we can see that for this period of time, we see that WAV load is running. So WAV load ran for 7.47 seconds. So almost the entirety of this. So we know, this is the thing that's taking time. And if we actually get a source code view here of the function, so we see that fopen takes a little bit of time. Reading in the file takes a little bit of time. Most of this stuff doesn't take any time. at least when we're doing this sample rate conversion, that takes so long that this other stuff is very small compared to that in terms of percentages. So even, the upsampling, virtually no time. Creating the filter, again, almost no time. But then we get to the actual filtering, and we can see that this is our hotspot, really. This inner for loop, and just computing all of these. So currently we're spending 88% of our time, 88% of 7.5 seconds on this single line of code. Of course, this is not a single instruction, but on this line we're spending that much time. So I think a good thing would be just to write this down first, so we don't lose it. So before optimizing, WAV load was 7.5 seconds at 8% on inner for loop, like that, which is, let's just compute what that is. 7.5 times 0.88, so 6.6 seconds roughly on the inner for loop. So that's sort of our starting point. I guess probably we can just create a new capture. We can have both open, but for now it's just good to have that written down. So it's this that we want to avoid doing for as many samples as we can. And so what do we know? We know that we have inserted L samples for every current sample that we have in our signal. We've inserted L additional samples. So basically, while this is probably not the best way of doing it, what I can do first is just if J, which is our, so I guess, well, so we want to skip no, so we have to think, just have to think a little bit here, because we're doing this for every sample, right? So we're not just doing it for the original samples, we're also doing it for the filtered ones. So we have to know the index that we're starting at, or that we're working on currently. So if we just do int32t, current sample index equals I plus j. If current sample index divided, or modulo L, so let's think here. So on the first one, this is going to be, so the current sample is going to be 0, and that's our original first sample, right? And so if we divide that, or modulo that by 2, we're going to get 1. No, sorry, 0. So how do you want to do this? No, sorry, of course, you're not going to get 0. You're going to get 2. I'm not thinking. So 0 modulo 2 is 2. 1 modulo 2 is 1. 2 modulo 2 is 0. So if that is equal to L, basically, or if it's not equal to L, because we only want to do this for samples that we know are non-zero, and all are going to be 0 except the ones that L. So if we sort of try to write this out here, so we have I'll do original samples are X, and then or zero samples are Z. So it's like going to be like this, right? So 0, 1, 2, 3, 4, 5, 6, 7, 8. So 0. Let's just continue here. So if 0 modulo 2 is unequal to 2, which is not the case here, is going to be the case here. It's going to be the case here. And then 3 modulo 2 is 2. What am I'm not thinking here. Maybe I shouldn't have started this video now. It's a bit, maybe my head isn't in the right place. I'm blanking here. Yeah, so we need to do, first of all, it's the number of, so our upsampling rate is, say, 2. So you're going to insert 1 sample, right? So it has to be L plus 1. So let's say you've inserted 2 samples, right? Because, so the sample count, the upsample sample count is the original sample count. If L is 1, you're going to do 2, right? So if we're upsampling by a factor of 1, my head is just not. Jeez. Is 0. Why can't I think? This is frustrating. Um, so in this case, originally L would be 2, and so you have to bump it up by 1, right? Because we have 3 samples in our upsample signal. So 0 modulo 3 is 3. 1 modulo 3 is I'm just like, what is, my head is just completely, alright, that's 0. Jesus. Sorry. I'm just completely blanking here. So 0 modulo 3 is 0. If it's not equal to 0, we skip. If it is something, if it is 0, let's just change this, or no, let's actually not change it. No, let's actually change it. So 0 modulo 3 is 0. 1 modulo 3 is 2. 2 modulo 3 is 1. 3 modulo 3 is 0, and so on. That was bad. So let's first try and run this to see if it still sounds the same. So yeah, sounds fine at least. So let me just I'm just gonna mute this when creating, because it does. So let's just run this, because this brings up a pop-up which is a bit loud. Then we can unmute. Now, just from this, it actually felt like it took longer. So maybe the if statement is not very a good way of optimizing this. Of course, this is just a basic idea, but I sort of expect, but now, oh, it's yeah, no, it's longer. I'm curious. Yep, so let's click this. Yeah, so it's a lot slower, which is interesting. So we see that, this is now taking a lot less time, right? It's just 7% of the time we're actually using this. But doing this, is hurting us. And I would kind of guess that so for 7% of this cases, or not 7%, but what is it going to be? Anyway, so we're doing both of these, so the comparison and this for quite a few number of samples, like a sixth maybe, or a seventh, but this we're doing for every, so, and maybe branch misprediction hurts us here. Um, even though all of these are known, maybe because they're not, const. I don't know. So that was obviously a very poor way of doing it. So let's try something else. So we know that the sample that we're starting from is going to be I, right? So for each inner loop, j is always 0 initially, so we're starting from I. So in first we can always in some cases we can skip, right? So if we want to skip, we want to offset j a certain number of samples. Say you're starting, if I is the sample is an upsampled sample, so it's a 0 sample, you want to skip ahead to a place, or you just want to set j so that your first sample is always going to be so that your first sample in the inner loop is always a non-zero sample, right? So what if we try to do that? So it's basically this again, right? So in 30t, let's just call it j offset is equal to I modulo L plus 1. So so if I is 0 and in our case L is 2, right? So we're down here again with this example here. The offset is going to be 0. So you're starting out, right? So but then let's say that I is 1. Well, the j offset is going to be 1 modulo 3, so that's 2. We set this here. So now the starting value of j is going to be 2, and so the current sample is going to be 1 plus 2, which is 3, so we go up to this sample instead. So we skip both of the two first samples, which is good. And then also the next thing is that we're going to not increment j one by one. Instead, what we know we can do is the distance between each, or the distance between non-zero samples is L plus 1. So we can set j to be this instead. So we can skip all of the 0 samples. So we don't actually need this for loop in this case. Or sorry, not the for loop, but the if statement. Sorry. So we've built that. Um, in theory, we could then just remove this. Let's just put this example up here instead. Like so, because now we don't have the if statement, and we've basically just changed our for loop to skip the samples that we don't care about, which should hopefully be better. So again, let's just try to run it. I'll be curious to see. Now that's, first of all, it sounds completely incorrect. So let's have a look here. That's interesting. It was a lot faster, right? But it's wrong. Maybe let's go into debug and, no, sorry, we need to set a breakpoint. In WAV here. Oops. I have a tendency to hit the mic sometimes, but okay, let's try here. So, L is 6. Right, so this isn't the example that we have here, but yes. The J offset is 0, right, because I is 0, modulo 7 is 0. I kind of don't see why this should be wrong. So let's see if we just jump in here. We have J is 0, right? So that's, how long is this? Okay, so it's quite long. What if we set it here instead? So we do one iteration, right? So now we come back here, so I is 1. So the J offset is 1. Oh yeah. So I see the, at least, so the issue here is, of course, that we want to so in the case here where I is 0, 0 modulo 3 is 0. So the J offset is 0. But when, no wait, when I is 1, 1 modulo 3 is 2. Hang on. So that's the first loop, that's fine. Second loop, I is 0, 1, sorry. L is still 6. J offset, 1. Why is J offset 1? I just can't. 1 modulo 7. I don't think today is my day, to be honest. It's not that either. So we have, sorry, yeah. So we have this minus this. obviously 1 modulo 7 isn't 6, it's 1, right? 8 modulo 7 is 1. 15 modulo 7 is 1, right? So in the second iteration of the outer loop here, I is going to be 1. 1 modulo 3 in our case here in this example is 1, but we want the number to be 2, so we do 3 minus this, which it becomes our j offset. So running this, skip to the second iteration of the loop, j offset is now 6, right? So I plus 6, so that's 7. And then for each iteration, j is going to increase by 7. So in the first iteration, it's 6. Next iteration is going to be 13, and so on. So if we put this back in release, turn off the breakpoint, and just run to check that it sounds correct. Which it does. So that's a good first step. Let me mute, and we can do another capture. We can just, no, let's just kill this. There's no need for it. But we'll do a new one. And, just by how fast it was when we ran it without the sampling or the profiler, it's a lot faster now. Like, a lot faster. So let's just have a look and see how much faster it actually is. So from here, we remember that our original, so after optimizing WAV load in its entirety now takes, if we open it up, 2.8 seconds. We can still have a look here in the source code. So again, less than 1% for this stuff, which isn't too surprising. But we can now see how actually some of the, so the deinterleaving is now starting to show up a little bit more. So this mem copy here, or so both of the mem copies are taking a little bit more than 1%. So in total, 5% by mem copy. 7% for some other stuff. I just want to skip beyond here, so let's see if there's anything else. Rather minimal here. So again, the mem copy during the deinterleaving. What else is, so we have a mem set. So this is the upsampling. The mem set is actually taking 2% of our time, and the mem copy in here is also doing that actually. But then once we actually get to the filtering, we now have that, computing the offset. We do that quite often. The actual for loop is a bit more. This is still the heaviest part, like clearly. But yeah. Storing into the upsample signal is taking more time. If we go back and look at this one, it still took a bit of time. It's probably taking just as much time as it used to before. It's just that this is now smaller in percentage, so something else has to increase, which is this. among other things. Yeah. So clearly this is still the hot spot. You know, we haven't gotten rid of it, which we never will, because that's that's the meat of the filtering or of the sample rate conversion. But it's less, and most importantly, the total runtime of the function is what do we? Yeah, from 7.5 to 2.8. I don't know how much. It's like a little bit more than 2. 2.6, 2.7. So it's still very slow, but at least it's faster. So if I just have a look at my to-do here, so we could probably update this a bit. So slow down songs during playback. Slow perform sample rate conversion during loading. We've done that. On WAV files, let's do that first. On WAV files, perform sample rate conversion on all formats. That's to do still. And then one of the things I want to change, or at least have as an option, is obviously now it's taking, or it's doing it on the entire file, right, at once, or during loading, or at load time. And one of the things I'd like to add as an option is to not load the entire file at once, and instead, read in a little bit more and a little bit more, and then each time you read in something, sample rate convert it and then play it back. So yeah, let's add that as well. Well, actually, let's keep that as slow down songs during playback is fine, but then support not loading entire sound files into memory. So this means load a part of the sound file, and upon finishing playback, load more. Now in theory you probably don't want to do it just like that, but at least that's sort of how it would look, right? Probably want to thread this, and then also ensure this works with the sample rate conversion. Yeah, so I think this is the one that we want to do next, but from what you've seen today, I don't think my head is in the best place to actually to continue working with this stuff. So I think I'll call it a quits there. We can remove the example. We can actually put this here. But it's not very relevant. We actually know that's a lot faster. So anyway, so that's kind of, yeah. Sorry about the modulo stuff. I was not expecting that to be that tricky today, but apparently it was. So we will go ahead and just commit this, and then I think we'll call it a quits. So code Bragi. Let's just have a look here. What's going on? to do and source wav cpp. Just have a look at the log. So it's sound player. So git commit snd ply. Optimize sample rate conversion. Skip computing the value for all 0 stuffed samples in the upsampled signal. When slowing down by a factor of 0.8 on slow dancing in a burning room, performance, the conversion time, wav load went from taking 7.5 seconds to 2.8 seconds in release mode. Yep. Let's do that. Yep, I think I'll just end there. I want to buy Superluminal, I think. I want to get a lot better at using it. It seems very good. And at least down the line, when I want to start doing quite a bit more interesting, I guess, maybe optimizations, I think it will be very useful to have. As just timing stuff on your own is not, you know, it's useful, but still. And I think you can get a perpetual license for Superluminal. It's not that expensive. Pricing, yeah. So you can get it's perpetual personal license for 60 euros. So that's not bad. So yeah. Anyway, thanks for watching, and I'm not sure when the next episode is going to be, but until then, bye.